Swayam Prabha. Digital India. Educated India.
Welcome back to this lecture series on foundations of cyber physical systems. So, if you remember, in the previous lecture we had been talking about how to analyze stability of closed loop transfer functions. So, we will just continue from there. So, let us say you have a transfer function of this form, a general form GS, where you have the output by input. This is given by polynomials representing the numerator and the denominator like this. So, the necessary condition for stability is that all coefficients of the denominator will have the same sign, but look, this is a necessary condition, it is not the sufficient condition. The sufficient condition is that necessary and sufficient condition is that all poles that we get from this denominator, that is RS, they are all located on the left half plane. That is what we discussed, that the poles are all located on the left half plane. So, if you have this satisfied, then you have the system as stable, and we have also already analyzed this based on these few examples of pole positions and all that. So, again repeating, the necessary condition would be like this. Let us say this is your polynomial here, right, and from this polynomial if you just create the factor and you find out that, well, what are the pole positions, these are all poles of the system, and for the system to be stable, all these poles must have negative real parts, and as you can see that for this to happen, the necessary condition is that the coefficients of the polynomial, these coefficients are 0, 2, Rn, all this, they must all have the same sign. For example, if you look at this, all the coefficients have the same sign. So, it is satisfying the necessary condition. So, I can say that this is stable, this can be stable, subjected to if we can also prove the sufficient condition. So, this is because it satisfies the necessary condition, all are having the same sign, right. But then you have to compute the poles and check their positions to be confirmed, and because you have to check the sufficient condition. But if you see the next one, you see here you do not even have to check the sufficiency condition. That means you do not need to compute the pole positions and check whether all of them are on the left half of the S-plane. Why? Because it does not even satisfy the necessary condition, which is that all the coefficients are having the same sign, because clearly you have some coefficients which are positive and some coefficients like the second one which is negative. So, this definitely is unstable. So, that is why here we are trying to say that why the necessary condition is also helpful to prove that some system is unstable. So, in general for LTI systems, what we can do is, suppose you have this representation of the system in this x dot equal to ax form, right. So, instead of transfer function, if you have this representation, what you have is you have the system matrix A, right, which is kind of giving you the evolution of the system starting from its initial state x0, right. So, what you can do is you can take A, which kind of represents the closed loop systems dynamics, and you compute the eigenvalues of the system. The eigenvalues of this matrix is same as the poles of the system, and you can just say whether the system is stable or not based on the nature of the solution without even solving the system model. So, again it will just be about the location of the poles. So, the way we compute eigenvalues of a matrix is the standard method, roots of determinant lambda I minus a, where I is the identity matrix. So, if you compute the roots of this polynomial, what you get is the eigenvalues of this matrix A. So, essentially they are the solutions of this characteristic equation, right. You get the determinant and you get the determinant polynomial, and you just so you can just set this thing to 0 and for the characteristic equation, and then from that you can just compute what are the eigenvalues. So, the roots that you compute from this characteristic equation, they are just the pole positions. So, again the condition is same, is just that you are starting from A instead of the transfer function representation here, So all the poles must have the negative real part, and similarly you have conditions for the unstable and marginally stable systems. If you are considering the linear system again, and you have multiple eigenvalues, let's say for each eigenvalue lambda, its algebraic multiplicity is this m lambda, and the geometric multiplicity is d lambda, then overall you can conclude this following, that the system is asymptotically stable. Asymptotically stable means eventually with t approaching infinity, the system must settle down towards the reference. Of course, for that the necessary and sufficient condition is for A, the eigenvalues must have the negative real part, and the system is neutrally stable if and only for every eigenvalue it has a non-positive real part and at least one eigenvalue as a zero real part. So this is the marginal stability situation, and this multiplicity with algebraic and geometric interpretations are same for every eigenvalue which has a zero real part. So for those eigenvalues which have a zero real part, for them these multiplicities must be same, so that's about at least one of the. So basically it's saying that, well, at least one pole is located on the imaginary axis and all the other poles are located on the, so at least one on the imaginary axis and all the others on the left of plane in terms of S-plane representation. So basically it's the same thing, but you are interpreting it in a matrix formalization. And of course the system is unstable if you have some eigenvalue that has a positive real part. So that's how you also can look at it. So that's about how you can create a system model. It can be a transfer function based model, it can be a state space representation with these matrices, right? And from that you can conclude by looking at this system matrix whether it's stable or unstable. Now suppose we find the system as unstable, we want to do the controller design, right? So the idea is you have this plant and you see that, let's say you give an unit step or some response input to this plant, and the output just wanders around. So overall you have an objective. The objective is, let's say this is the target reference with an input step. You want the plant to settle down here following some trajectory criteria in using and it must meet some settling time pattern. So you want a response like this or maybe a response like this, depending on what is your objective. You may have a specification that the maximum overshoot should be less than this, the rise time should be less than some value this, or the settling time should be less than some value this. So this may be your control design criteria, and as you can see that just the plant by itself doesn't meet any of this criteria, and the plant by default may be unstable. So what to do? As we have discussed that our key objective in this series of lectures in this week had been that, well, we will learn how to model plants mathematically, and we will learn some simple techniques of controller design, so that when we put the plant in loop with the controller and derive an equivalent system out of this, this system is destined to satisfy this requirement. So this is my requirement, this is the plant, so these are the two things given. I must design this controller so that the closed loop system satisfies this requirement. That's the problem here we are talking about. So consider that you have the linear system which is given like this. So this is the state equation and this is the output equation. So you have let's say for n-dimensional systems you have an n-dimensional vector of the state, and you have the corresponding ABC matrices. Okay, and let's say you have an objective that the output must settle down around some reference R with t approaching infinity. The question is, how do I design this control input U? We are still talking about continuous domain systems, so we will try to design continuous controllers. So if you just take a flow diagram based view here, so our system is going to look like this. So you have AX plus BU, which should give you this X dot, right? If you integrate it, that's your X. If you apply the transformation C, that's your output, right? And if you apply this K, on x, what you get is this value kx, right, and then you may have some feed forward gain f here on which the reference is acting. So here you get kx, here you get fr, right, and from them you get the overall control signal. So that's the thing here. So the idea is when this loop is open, you don't have this. So all you have is a system x dot equal to ax, right. So if the loop is open, you just have this much happening here. There is no u. Now let's say we want to close this loop, and we want to design this controller gain k so that we meet those objectives that we talked about. So you will have this equation. So earlier none of these things were here, right. So this was pretty much your system. That's why x dot was just nothing but ax. That's what was earlier. But now we are bringing in all this additional stuff right here with the gain, the feed forward, etc., etc. And we want to stabilize this loop so that this response y is approaching the reference r. We want this to happen. So if you look at it, x dot is if you just look at you have the equations. X dot is nothing but ax coming like this, and then you have x. If you see ax plus bu, but as we saw that u is nothing but kx plus fr, right. So bu, if you see, it is bkx plus bfr, and you have then x dot equal to a plus bk multiplied by x plus bfr. So that's your dynamical equation, and the output y is this cx. So the question is, how do I design this k and how do I design this feed forward gain f so that we have this requirement satisfied that eventually the system output must stabilize around r. We need that to be satisfied. So what we will now study is a very well known, the most simple way of controller design, which is designing this gain k by pole placement technique. So if the system considered is completely state controllable, so we will understand what that means. Then what we need to do is we will design the gain k in such a way that the eigenvalues of the closed loop pole must be positioned in a location so that the desired behavior happens. So that's kind of our target. So let's understand what we are really trying to do here. So you see, without this k and f, you had this system dynamics defined by a, and that was something I was unhappy with. So I am now bringing in this k, and what should be k and what should be f is in my hand, right. Now let's say I have already designed k and f, then the resulting dynamics of the system, as you can see, would be given by this matrix, right, a plus bk, or I mean depending on how you look at it, ideally you can, I mean in most books what you will see is this is negative, and that's an a minus bk. So and actually let's just go by that standard convention. So this is a minus here, okay. So minus kx plus fr, this is this, okay. So the point I was trying to make is, for the open loop the dynamics is dictated by a, for the closed loop the dynamics is dictated by a minus bk, right. The trick in this entire situation is you design k in such a way that for the matrix a minus bk you should have the poles located at suitable positions so that you get the desired behavior. So let's say for a, For A, which was just given to you, which is the unknown plant, you may have poles located here, let's say here, one here, etc., and that was giving you some bad behavior. But now you have an opportunity to modify the closed loop by bringing in K. When you bring in K, the closed loop equation is, the closed loop matrix is this. This is what is deciding how the system will behave. So you have an opportunity to design K such that your eventual matrix becomes such that its eigenvalues become such that the corresponding poles are located at some good positions. Good positions means some positions which satisfy your requirement. So that's the simplest story of pole placement based control design. So what you do is you decide where you want to place the poles, because you know that if the closed loop system's poles are here, here, and here, then the output behavior will be nice, and that's what I want. So let's figure out what K should be, so that for this A minus BK, the poles are located here and here. That's all we are doing in pole placement based controller design, nothing else. So let's continue with this intuition. So the target is to set K so that you get the eigenvalues of A minus BK located as you want them to be. So this technique begins with the determination of the desired closed loop poles based on the transient response and or the frequency response, such as the damping ratio, speed, etc. So you are given some requirements. Let's say somebody that you have been told that, well, you must design the gain K in such a way that the closed loop response should satisfy this rise time, this settling time, this maximum overshoot, etc., etc. So from those things you can have an estimate that, well, if I place the poles here and here, these things I will satisfy. Then all you do is you bring in the mathematical machinery which will ensure that A minus BK's eigenvalues are located precisely at those positions. So here in this case we limit our discussions. We consider that all states are measurable and they are available for feedback, which will just make C as a identity matrix here, so that essentially we are saying that it's a full state feedback system. All the X outputs are available for K to operate on. We will soon see in our later lectures that this is not what we get in principle, and from the output you need to get the estimate of state, but we'll cover those complex things later on. For many situations we can also have full state feedback and we just work with it. And we can also make one simplistic assumption in certain cases that, well, the reference input is 0. It may depend whether I want to design that feed forward gain or if I don't want to design that feed forward gain. Okay, and we will also see that, well, how the expression for the feed forward gain can come. Okay, so the control signal and the output, for simplicity, we consider these to be scalars, and the systems are single input single output systems, and the reference is 0. And we will demonstrate the following approaches for determining this gain matrix K. One is called the direct substitution method and the other is called the Ackermann's formula. So for direct substitution, what you do is you first check this thing, this matrix, and look at this state controllability matrix and check its rank. What does this check tell you? It tells that, well, if this controllability condition is satisfied, then I have a guarantee that system is controllable. That means it is indeed possible to design a controller which will ensure that in the closed loop the plant and controller combination will be steered eventually, will eventually steer the system in the desired trajectory. And then once this check is done, you define the feedback gain using these unknowns. So your objective is to figure out what are these unknowns. And then what you will do is, well, you have already identified what are the desired positions where I am going to put the poles. Now based on those desired positions, you can write this characteristic equation. Let's say I have decided that, well, the poles should be at positions lambda 1, lambda 2, lambda n, like that. Then that means for the target system in the closed loop, when I have write the transfer function, the denominator of the transfer function, basically the desired characteristic equation, should be same as this left hand side. And we have this thing, right? We have this unknown gain values. Now putting those unknown gain values here, if we take this determinant, we can generate this characteristic equation like this. So this is what I want to happen, and this is what I have with sub unknowns. So that's how we will proceed now. So just a bit on controllability. We will talk about that. Okay, first let's proceed for this with an example here. So let's say this is your system. So you have A, B given to you, okay, and you are generating a single input, single output, okay. So U is minus kx. Let's say for this you have the desired pole positions at lambda 1, lambda 2, and lambda 3, and the first thing you do is you check the controllability. That means you generate this matrix. You know what is A and what is B. So and the dimension of the system is n equal to 3. So using these values of B, A, and n, you can create this matrix Ct, and you can check whether the rank of this thing is equal to the dimension of the system. So you can check if the rank of the matrix is equal to 3, which is true. Then we will say that, well, the pole placement is indeed possible. Now let us go about doing these things. That means equating the characteristic equation with the desired one. So first we have assumed these unknowns k1, k2, k3 to comprise the controller k. So with this k, which is unknown, I can write this determinant, right, Si minus A plus Bk. By the way, what is this? All we are doing is, so as we discussed, right, this is your system, and for this system, like we said, this is the closed loop matrix which is governing the system. So I want to figure out its eigenvalues, and the eigenvalues would be nothing but so if you remember, for a matrix A, the eigenvalues were given by these solutions to the characteristic equation of this thing, right? I mean Si minus A. Now in place of that you have A minus Bk. So for that you have to compute Si minus A plus Bk. You want to see that, well, what are the roots of this polynomial. So to compute the roots of this polynomial, you have to create the corresponding characteristic equation and set it to 0, right? So that's what you do. You take the determinant over this here and see what is the corresponding characteristic polynomial here. So Si becomes this, and minus A plus B, and this is your unknown k, right? So this will lead you to this is going to lead you to this kind of a characteristic equation corresponding to this closed loop A minus Bk matrix, right? This closed loop matrix, and you want to know what are the roots of this equation. So, and what you really want is the roots must be this, this, and this. This is what you want. So your desire that this characteristic equation has roots as follows can be easy to achieve. So all you do is, well, if these are the roots, then they together can give me this characteristic equation, which is S minus lambda 1, S minus lambda 2, S minus lambda 3, and this must be equal to the left hand side, which is the characteristic equation derived from Si minus A plus Bk, right? And so they must be equal, and if they have to be equal, the coefficients of the different polynomial terms in S, they must be same, they must be equated, right? So S cube's coefficient must be here like this, right? So for example, if you see, you must have 14 equal to the coefficient of S square, because here 14 is the coefficient of S square here. So 6 plus K3 is 14. Similarly, S coefficient is 60, that is equal to 5 plus K2. So from this you can solve and get K3 equal to 8, K2 equal to 55, and K1 equal to something. So essentially what you are getting is, you have a system of equations with the number of equations same as the number of variables, and that would give you a unique solutions, and that would give you these values of K1, K2, and K3, which gives you essentially the controller, right? So the gain thus designed to place the poles of the closed loop at the desired location are now computed by equating this characteristic equation of A minus bk, its coefficients, with the characteristic equation coefficients of the desired closed loop pole positions, and their and the resulting target denominator of the transfer function. So it's very simple, as we can see. Just to summarize, all we did was we are thinking of this target system A minus bk, right? And for this target system, we created the symbolic characteristic equation here, and for this symbolic characteristic equation, we equated that with the form that we desire it to be in, which was this, and then we just equated coefficients, and from these coefficients we calculated what should be the control gain values. So that's about it, right? So that's about the way in which you do direct substitution, and the other there is also another technique which is basically the same one, but it kind of tells you how to do it using just matrix multiplication standard formula. So the first step is same. So you check the controllability using the similar idea that we gave, and you choose the desired closed loop poles at these locations like we have discussed here, right? And then you just apply this Ackermann's formula. Now what is the formula? It says that, well, k equal to minus of this all zeros then 1, then you have this gamma inverse times HA, where is gamma is nothing but this matrix, well, where A, B are all given to you and you know the dimension, and HA is nothing but this matrix, okay? So that's it. So essentially this is like automating the previous method. So all you are doing is you are given these lambdas, right? You know A, B and the dimension, right? So you just use this formula, and from this formula you will directly get the pole position. So let's say an example. Suppose this is your system, and this is your target values of lambda 1, lambda 2 and lambda 3, and well, first you do the controllability check like we discussed and see that the rank is equal to the dimension, hence this is indeed possible to design the controller. You compute HA here, okay, and the gamma value is already this one that we have, right? So HA is based on this A and lambdas, so you get this equation, right? And then K is nothing but this matrix, then it's followed by gamma inverse and then is HA. So it's essentially automating that entire process of direct substitution, and you directly get K. So that tells you that, well, what should be the pole positions, and you can see that they are matching. So of course some of these examples have been taken from well-known lectures and slides available. Fine. And now consider the situation where your R is not 0 and you indeed require to design that feed forward gain F. Okay. So I mean, let's say, so this equation is U equal to Kx plus Fr. Okay. So your equation x dot is this, y equal to this, and you can just solve and figure out what R should be. So let's see what should be if you take Laplace transform here. Let's see what you get. So you have xs. Okay. From this it is easy to derive this thing because of course this would give you s xs minus a minus bk xs. If you take xs common, si minus a minus bk. This sign really doesn't matter, it depends on how you are modeling the k. If you take u equal to minus kx in your initial model, just proceed accordingly. So don't really worry about this. In our previous example, for example, in our previous derivation, we took that minus because in most books you will see that that's the standard that is followed, but it's just a modeling issue. So this is it, right? So once you know that, well, the transform is this, then you can just apply si minus a minus bk inverse on both sides to get to this line, right? So once this is the case, you know x, then you can just see what is y. So y is c of xs, so that's just this line. So c times si minus a minus bk inverse and then you have the B, F, R, S, because B and F are going to be constant and R is a function of S here. So in general I can say for the closed loop is just the Y by R, right, the input output by the reference input. So that function is this, right. Now the question is, how do I choose F? You must choose F in such a way that y which is a function of time, it must approach some constant R, the reference, with t tending to infinity, right. So you can apply final value theorem here, which would tell you that, well, this limit is nothing but R. So you already see this is your expression of ys. If you apply this limit, it will be it, and if you equate it to R, right. So then eventually what you will get is, and R is, if you set R as 1 here, I mean, of course this should be equal to R, and then Y by R. From that, by using this theorem, you can generate F to be equal to this thing here. So you see this form remains. That's what you have here, and then if you apply the final value theorem, you eventually get a F of this form. So in case you really have the reference, because if you remember when we did the earlier part, so we considered the reference is 0, but of course it is possible that you have a reference signal, and in that case you will need this feed forward gain, and the way you can design this feed forward gain would be to use this formula like right here. So with this we will end the lecture here. Thank you.